Hi everyone. I guess we're live, so I guess I can start. I hope you all see this funny slide that I made because I have a great sense of humor, because it's really capturing what this talk is about, and it's about exponential speedups in quantum algorithms, how you can sometimes lose them, and what you should be doing to make sure that this doesn't happen to you again. But before I go on with the talk, which is much more boring than this particular picture here, I would just like to thank all the organizers, like Sean and Robin and Bob and Konstantinos, of course, for the invite. And a little bit of a warning: it's a little bit of an outlier talk, not because it couldn't be connected a little bit better to language processing. It's just that we haven't gone around to doing it yet. So the boring slide says that today's talk is about quantum advantage for topological data analysis. And it's, I have to emphasize, joint work with Casper, Jurek, and Chris Cade, and I thank them a lot for doing most of the work in what I'm going to present. So the outline is, I'll tell you a little bit about the broad topic of the talk, why I care, why you should care about the issue, about topological data analysis itself, because I'm kind of assuming that most of you don't do work with it every day, and then a little bit about the quantum algorithm we use to solve it, and something we can say about the hardness of the problem that we're actually solving. And it's going to be one of those talks where I spend like 90% of the time introducing the topic, and then maybe in 10% of the time I simply list what the results were, because that's what the constraints make me do. So first of all, I would like to highlight that I'm sure that all of you are aware that quantum machine learning, or quantum enhanced machine learning rather, is sort of pretty much in a very popular phase right now. And I would like to say that I would like to argue that in part it's because machine learning is more popular than it ever was before, and in part there's a good reason for this, and that's because quantum effects can help in many interesting different ways in doing machine learning in some better or more interesting way. Like in the olden days, one of the first ideas we had into how to use quantum computing was to speed up the training aspect of machine learning. So like the optimization that has to be done to train your model typically can be computationally intractable and hard, and people thought about using various types of quantum processing to ameliorate that. One of the most recent things in quantum machine learning was the design of sort of new models, which can be realized using quantum circuits, but are somehow classically intractable. And here, of course, talk about variational parameterized quantum circuits, which can serve as a proxy for a neural network. And this is like all super exciting. And between this first two bullet points, this one and this one, there was this wonderful period of a few years. I'm going to say from, let's say, 2012 until 2018, where the idea was that quantum machine learning is going to be helped by quantum mechanics in a linear algebraic sort of way. So when your data is really, really big, you need to use quantum mechanics because it's going to allow you to process stuff polylogarithmically in the size. And this is what I want to talk about. This is where my algorithm is going to be. So I'm going to give you a few more details on this, but not too many. So the basic idea of this quantum linear algebraic flavor of machine learning is to really interpret quantum mechanics as linear algebra in a very literal sort of way. So like if I have an n-dimensional data point, so a vector of n real numbers, I need something like 4n bytes to store it in my memory. Whereas if I simply encode all these real numbers in amplitudes, of course, up to normalization, somehow it all fits in log n qubits. And then essentially whatever I do to these log n qubits, if I do it in a standard polite quantum computing sort of way, it's going to be polynomial in this quantity, right? So it's going to be polylogarithmic processing of my data vectors. So it was a really, really nice idea, provided you know how to generate these vectors and how to process them exactly and how to read it out. But the catch, the important thing was we found applications for this, right? And many of them sort of worked really in this machine learning sort of context. And in part because of many of the restrictions you get when you use quantum mechanics this way, somehow hurt much less in the quantum context. So specifically, we used a QRAM to generate these, to use these data vectors and generate them, and everything was efficient as long as my data was somehow living in a low-dimensional manifold, linear manifold of the entire Hilbert space. And then in 2018, and of course the hope here was that we found sort of a fountain of these magical exponential speedups, and people have started producing really quite a large frequency of algorithms for machine learning with such an exponential promise. But then in 2018, some smart individuals figured out that you can also interpret probability theory as linear algebra verbatim, and that you can encode, exponentially many probabilities, so positive, negative real numbers, into the probability space of, logarithmically fewer subsystems. And you can also process them using stochastic maps, not unitary maps, and you can sample to somehow estimate certain inner products. And this idea worked well. In fact, it worked too well, in a sense that under the conditions where the quantum things work well, it just so happens the classical ones did as well, in that we got classical exponential speedups in essentially all the cases that we had in the quantum case as well. So yay for very efficient classical algorithms, but of course, classical exponential speedup means no quantum exponential advantage. So it was somehow lost, and we were all very, very sad. So the fair question here is, are all quantum linear algebraic flavored quantum machine learning algorithms dequantizable in such a way? And that's what I'm gonna sort of answer. But before I can do that, I need to tell you about topological data analysis. So I'm assuming that most of you know quite a bit about machine learning. And what I would like to tell you is like what flavor of machine learning topological data analysis is. And you should really think principal component analysis and not neural networks. So it's sort of a feature extraction method rather than a classification or a classification type algorithm. And I'm going to liken it to principal component analysis. So you probably know, so this is nothing but singular value decomposition, which takes a cloud of points, looks at its grand matrix, and somehow identifies the directions which explain most of the data. And there's going to be your first principal vector, and you're going to have second one, and up to however many you have, depending on the rank of your matrix. And typically use it to compress your data into a smaller space, smaller dimensional space. But you can also think about the singular values as being the things which characterize your entire point cloud, right? So these point clouds are different because they have different singular values. So it's sort of a feature extraction thing. And it's cool because it's invariant under rotations, translations, rescaling, so somehow robust to various perturbations of the data. But of course, data can also bend and stretch and do things like that. And maybe I would like it to be robust under that as well. And that's what topological data analysis does. So it extracts the so-called persistent topological properties from point clouds. So which properties in particular? It counts holes. So it's really algebraic topology, the basic thing. So to explain what I mean by this, if you think about a torus as a solid, sort of solid object in some ambient space, to it I can assign 0 holes, 1 holes, 2 holes, etc., ever high dimensional holes in the following way. The 0 holes are simply the number of connected components. So that's 1 in the case of the torus. The 1 holes are going to be all the non-contractible circles, and I have 2 of them, like the 2 main circles which define the torus. And the 2 hole is going to be the void inside the torus. So that would be the thing you eat when you eat a donut, right? You eat the potential 2 hole of the donut. So the topological data analysis pipeline has sort of 3 main steps which are iterated. You start with a point cloud. I have n points. The n is an important quantity which live in some higher dimensional space in principle, but this dimension doesn't matter for what I want to do. And then I'll use some process to connect these points into sort of a solid object. I'm going to build something called a simplicial complex. In my case, it's going to simply be a graph. And what I have to decide is when do I connect the points? And this is done by some coarse graining epsilon. So I'm going to say that if my points are, let's say, epsilon close, then I connect them, otherwise I don't, right? And once I have my solid object, I can extract my number of components, 1 host, 2 hosts, etc. And this vector beta 1 up to the number of points is what fully characterizes all the features that I care about this entire object encoding the point cloud. And I can do that at various coarse grainings and then study sort of the resulting diagrams telling me which holes are really there and which are sort of maybe just an artifact of how I process my data. Okay. Now, before going further with all this, why should you care about topological data analysis? It's a very, very fair question. And the fact is, it's sort of a new method. I mean, the idea has been around for a long time, but it's computationally very, very difficult. And we don't know too much about it, in all fairness. But in the last few years, there's been sort of an ever-increasing number of papers using it for various hard topics, including even characterizing multi-party entanglement. But for this particular conference, I did my homework, and I did more than 10 minutes of Googling to find a bunch of papers which use topological data analysis for natural language processing. So I think there might be a number of connections to be made here, which are still up for grabs, through quantum computing or directly. So going back to what I really want to do. Story so far, once I have a mesh or a graph, something which describes this complete object, I need to read out the numbers of holes of various dimensionalities. So in particular, point cloud plus my choice of epsilon defines a graph. And this graph is going to help me define the number of holes. I will not go into details how this is exactly done, but let's stick with this for now. And now, how do I actually read out the number of k-holes? Well, a bit of math, something called Hodge theory in topology and works of Ekman, show that you can actually count these holes in a linear algebraic sort of way. That is, the number of k-dimensional holes, which is also known as the kth Betti number, is equal to the kernel dimension, so the dimension of the null space of an object called the kth combinatorial Laplacian. So Laplacian is a fancy adjacency matrix. Kth combinatorial Laplacian is a adjacency matrix of k cliques. Of k cliques are all the complete k size subgraphs of your graph. And we need to compute the nullities of that matrix, so the kernel dimension of that matrix. That's our task. Just to give you a bit of a flavor of what these combinatorial Laplacians look like, so given a graph G over n vertices, the kth combinatorial Laplacian is a matrix enumerated by all the k+1 cliques, so all k+1 complete subgraphs of my graph G. And I know that somehow the entries tell me something about whether the cliques are connected or not, and ask me later if you care about finding more details. It's a Hermitian matrix and it's also sparse, which is nice. And one thing you can immediately see that it's a combinatorially sized object, right? Its size is at most n choose k plus 1, in fact. So when k scales with n, this entire thing is a combinatorially large super polynomially sized matrix. But I compute its entries for something which is just n sized. And this is the sort of thing you want for efficient quantum algorithms, that you can somehow generate on the fly these things. You don't need quantum RAM or anything like that. So, story so far. You give me a point cloud, a bunch of data points. You tell me an epsilon. This specifies a graph, or rather a simplicial complex, which in this case will be a graph. This graph induces some large matrices, which are called the combinatorial Laplacians. They're specific to the graph and specific to the k, the dimensionality of the hole that I care about. And I need to compute the Betti numbers with the nullities of this matrix. So what I will be doing next is computing not really the nullity, not really the number of zero eigenvalues, but rather the frequency. So the ratio of the number of zero eigenvalues versus the entire dimensionality of my matrix. Okay, and this problem I will call the topological data analysis problem. So the quantum algorithm, it is not super important for what I want to do, but I will tell you because it's actually remarkably simple in principle. It's the algorithm of Lloyd, Garnerone, and Zanardi, and it uses two main subroutines. One is called Hamiltonian simulation, which, if you give me a sparse axis or somehow succinct description of a Hermitian matrix H, like the combinatorial Laplacian, you can generate the unitary time evolution under this matrix understood as a Hamiltonian. And then what you do is, well, you choose a random eigenvector of your matrix H, and I estimate its eigenvalue. Of course, I have to do that to some precision, and I'm kind of assuming that I'm precise enough to distinguish between the zero eigenvalue and the first non-zero one. And if my eigenvalue is zero, I increase my counter. And I do this polynomially many times, and what I'm returning is a frequency of zeros, which is estimating my normalized nullity. Simple as that. Now, of course, you complain. You say, but where do you get the eigenvectors of the Hermitian matrix? Well, you're right. It's hard. I wouldn't be able to do that. But note that I need a random eigenvector. So instead of having a particular random eigenvector here, I can actually plug in a maximally mixed state, which has infinitely many resolutions, one being in the eigenbasis of H. And I just run the algorithm pretending that it was a random eigenvector, and it all works out. So that's really, really cool. So this algorithm allows me to estimate the nullity of a matrix H, provided I can, of course, do Hamiltonian simulation on it. And here's a little bit of a catch that unfortunately I don't have time to go into in much detail. The combinatorial Laplacian, if you recall, it's enumerated by the k+1 cliques. So I need to know something about the number of the cliques of my graph. And the problem is that enumeration of cliques of a given graph is already NP-hard. So I have to come up with some indirect way of getting this matrix. And I have to hope that the number of cliques that I have is actually either very small or very large. In both cases, I can make it work. So there's some restrictions when this is actually efficient. So in more details, what the LGZ algorithm does, it approximates the estimate of normalized Betti numbers. The epsilon is sort of telling me how precisely I'm estimating. And the runtime of the algorithm is polynomial in the original graph, proportional to the precision that I want, squared. And it kind of depends on how many clicks I have in my graph. If I have few, then it can be very expensive, but if I have many, then it's cheap. Now, the best classical algorithm we have is actually n to the k. And it goes through essentially through diagonalization. We actually get the Bethe numbers, and we don't know how to do that much better than that. So again, this thing here is exponential in k. The LGZ complexity is independent from k. And this is where an exponential separation comes into play between what we do quantumly and what we can do classically. So now we know that classical algorithms are slow, and simulating what the quantum algorithm does is probably slow, because in fact, what it's doing is sampling eigenvalues, and this is in fact BQP complete. But can we prove that the actual problem of topological data analysis, which doesn't care about arbitrary matrices and doesn't care about sampling eigenvalues, just zeros, is it hard? So this is what we do. We formally define a bunch of computational problems. The one that you should really care about is the approximate normalized Bethe number estimation, which is what the algorithm of Lloyd et al. Actually does, and well, is used for. And the core of the LGZ algorithm, which is what the algorithm actually does, and that's estimate the spectral density, so the fraction of eigenvalues below some small threshold. Okay, this is what the quantum algorithm allows me to do. And you can easily conclude that, well, if I can solve LLSD, this low-lying eigenvalue spectral density, then I can also solve ABNE, the Bethe number estimation, whenever I can actually simulate the combinatorial Laplacian. And the actual Bethe number estimation is solvable by ABNE when my gap between the first and the second smallest eigenvalues is 1 over poly. And you can show that very often it is. And note that, let me introduce the color notation. The red stuff, this is all about the combinatorial Laplacians. The blue stuff is all about counting frequencies of eigenvalues, the zeros, in fact. So, well, now I have to admit something to you, and I'm confident in doing that because we're in such a private atmosphere. Of course, solving LLSD is not the same as estimating Bethe numbers approximately. But it is the closest thing that we could actually fully characterize in terms of computational hardness. So there are some gaps in the final result, which I will clarify again. So our main hardness result is that the low-lying spectral density problem is DQC1 hard. DQC1 is the one clean qubit model. So general quantum computing, you prepare the register in an all-zero state, apply a unitary, and measure a single qubit. DQC1 is you have only one qubit in the zero state and everything else is in the maximally mixed state. So it's a restricted model relative to full-blown quantum computing, but we still don't know how to simulate it classically in polynomial time. And some very smart people claim that it's probably not possible. So it's much more, we're much more sure that this is not going to be dequantized than what we think about the Bethe numbers a priori. So we've done a little bit more extensive analysis of the relationship between all these classes. I will not go into too much detail here, but the point is that, maybe this is the summary. If the combinatorial Laplacians themselves are sort of a very rich family of matrices, so they are, I just don't know if they're rich enough, then topological data analysis itself is just as hard as simulating the one clean qubit model. At the moment, we don't know that, but this is providing some evidence that the topological data analysis problem should be hard. But also this entire diagram kind of motivates studying two generalizations of the entire topic. One has to do with, combinatorial Laplacians. We had to learn a lot about them, and they're interesting objects. So maybe they're also interesting. Maybe there are other things you can do with them that has nice quantum algorithms, but which don't do eigenvalue counting, but maybe something else. And on the other hand, we know that playing around with eigenvalue counting is DQC1 hard. So if you find uses for that, which can have an input any matrix, not just a combinatorial Laplacian, well, that's already non-dequantizable, so it's kind of safe, right? So we kind of started there and came up with a couple of results that I'm going to just quickly share with you. Number one has to do with this problem of random click counting. So I'm saying it's a result, but it's actually, okay, we found a paper which says the following. If my graph is dense enough, so it has sort of approximately 1/2 of all the possible edges, then their combinatorial Laplacians have many clicks, exponentially many clicks, and in fact, click sampling becomes efficient. So in the TDA case, this just says that when my epsilon or my coarse graining is high, when my thing is very connected, then I can random click sample efficiently. Second thing is combinatorial Laplacians are important in complex network analysis. And people have used sort of quantum-inspired methods to analyze networks. And one of them has to do with computing Renyi entropies of sort of normalized combinatorial Laplacians. And it just so happens that if you think about it a little bit, you can find out how to do this quantumly as well, efficiently. Moreover, for certain Renyi entropies, it so happens that this problem is also DQC1 hard, if the combinatorial Laplacians are a rich enough family. So sort of the same caveat as before. So it kind of motivates us to study these combinatorial Laplacians a bit more. On the other hand, if I don't care about combinatorial Laplacians, but I want to sort of get the most bang out of the hardness of estimating zeros, well, estimating the nullity is the same as estimating the rank. And estimating numerical rank of a matrix is a really, really famous problem, very, very important in a lot of data analysis things, where, for instance, if you want to really put your data in a lower dimensional space, these algorithms typically on an input take the estimate of the rank. So you kind of have to have it. And what we show is that, well, if my matrix is given in sparse access, then I have a guaranteed exponential separation between classical and quantum algorithms, conditional on DQC1 not being classically simulatable. And if you don't, it just so happens that it suffices to have triplets of row and column and the value of the matrix stored in QRAM. So all triplets where the value is not zero. So it's not really sparse access, it's something a little bit less. And it's still DQC1 hard. So it's kind of a really cool result. And last thing that I want to tell you, and I'm going to just spend less than a minute on that, is, okay, so is this the quantum killer app for near-term quantum computers? And for that, I have to, consult my four-leaf clover of NISQ killer apps. Does it work with small quantum computers? Does it work with restricted depth and architecture? Is it important? And is it tolerant to noise? And in short, with respect to architecture depth, well, we need to do Hamiltonian simulation, but so do most quantum chemistry people. So whatever progress they get in getting quantum chemistry to work, non-variational quantum chemistry, we can use their results as well. Is it important? Probably. We don't know. Topological data analysis is new, but it might be a game changer. Does it work with few qubits? The vanilla implementation provides a quantum advantage at 150 ideal qubits. We think that we can kind of bring it down to 110 by clever pre-processing. Is it robust? To some extent, but not all the way. If you perturb a matrix in some generic way, then you kind of can compute how much you're perturbing the eigenvalues. And we really want to protect the zeros. So if my perturbation is below the gap between the zero eigenvalue and the first excited eigenvalue, then I'm not changing my outcome. And I'm probably not changing my outcome much, even if I perturb it a bit more than that. And with this, I end. So in summary, I've shown you the quantum linear algebraic algorithm for TDA, topological data analysis. That problem is probably hard for a classical computer, so cannot be dequantized. But there are many, many interesting spin-off problems. Some of them are intrinsically hard, and some of them we have to work hard again to prove them hard. And it's not a bad candidate for sort of a NISQ killer app. So thanks with that. I'm super happy to take whatever questions you have for me. And if you don't have the time for questions, please drop me an email. I'm really, really happy to respond to anything.
Okay, thank you, Vedran. Really nice. Alex has got a question. Could you give an intuition of why this algorithm is DQC1 hard and not, e.g., BQP?
Yeah. Well, I mean, if you recall, the simplest synthesis, I don't know if are you still seeing my screen?
Yep.
Yeah. Note here that I said that I can put in not an eigenvector, but a maximally mixed state on input. So some of the algorithm that I want to run by default takes a maximally mixed state on input. And the rest, I need clean qubits to do a phase estimation, but it turns out that sort of very few qubits is enough.
Okay.
So maybe that helps, right? That I don't have to control what these things are.
Okay, thank you. Just waiting for any other questions to come through. I know you said you didn't know too much about it yet, but could you indicate roughly how you imagine this being useful for NLP? I mean, topological data stuff generally.
Well, I mean, the number one thing that I would say is I would have to go into these papers and figure out exactly which aspect of NLP is actually tackled by topological data.
Yeah.
And the second thing is, this is such a weird thing. If you think about diagrammatic calculi, it certainly looks more about topology than geometry, right? On
Yeah.
some fundamental level, right? So I'm wondering if there's some connection to be made there, but this is like really, really far-fetched. And the third thing is to the algorithms themselves, right?
Yeah.
But you know, the low-hanging fruit would be to take a look at what these guys do, and then see whether you can connect somehow. Ideally, get rid of the Hamiltonian simulation part. That would be nice.
Okay. I don't think we have any more questions. We thought, well, maybe people are heading to the next talk around now.